And this will sort of then round out a sequence of lectures on Stiefel-Whitney classes. We're going to understand them from different perspectives. We're going to have another application to group cohomology. Then we're going to switch to Chern classes and get some applications there, some of which have their analogs in Stiefel-Whitney, but I wanted to go ahead and give them in Chern classes. Okay, so where are we? We have we've shown that the cohomology of the infinite Grassmannian is a polynomial algebra. And so we last showed that if we took the cohomology of the Grassmannian of n-planes in R infinity, then that actually injects as the polynomial in symmetric polynomial algebra generated by elementary symmetric polynomials in the cohomology of a product of in product factors of RP infinity. I'm going to call this equation star, this injectivity. Remember that this composite here is induced by the classifying map for a direct sum of these standard line bundles over RP infinity. That direct sum gives us a rank n vector bundle, and on cohomology the map goes the other way. So that's a map from product of RP infinities over which these line bundles live. So the direct sum lives over the product. But on cohomology, we pull back and we get this composite, or this map whose image is a polynomial algebra. Moreover, the I-Stiefel-Whitney class of the universal bundle, so it's sort of the universal I-Stiefel-Whitney class, goes to the ith elementary symmetric polynomial. And what we can also say is that, in fact, 1 plus W1 plus Wn gamma n. And we could even call this W naught of gamma n. So this total Stiefel-Whitney class goes to, if you remember how we made the calculation, goes to a product of 1 plus xi, the ith factor. So this is the polynomial algebra on x1, xn. Here, the sigmas are in, sigma I is in degree I. Here, all the xi's are in degree 1. So I'm going to call this second fact star prime. Okay, so that's what we showed. And again, what we did is we thought about this as an upper bound for the cohomology of the Grassmannian, and it maps homomorphically onto a polynomial algebra with generators, one generator in each degree from 1 to n. And then you can calculate ranks and you see partition functions. And so that gives you a lower bound, and then the cell structure gives you an upper bound, and they match. So that's the cohomology. So this calculation is key for in that application. Well, let's state the following theorem, which will be our first main step in the proof of Whitney sum that I now prefer is that this calculation is equivalent to the Whitney sum formula. At least in light of the classification theorem, but of course we can assume anything that we've already shown to be true. So, so this will be a way to establish the Whitney sum formula then through establishing the calculation star. So let's go ahead and prove this. So we did half of this already, which means then that if we were trying to prove the Whitney sum formula from star, that would be circular. But again, we're going to prove formula star independently. But in the context of this theorem, this is just recalling that if you have the Whitney sum formula, then and in particular with what we immediately get is star prime, which we see above. Whitney sum formula says that the total Stiefel-Whitney class would just be the product of these 1 plus xi's. And we used to show that there were no universal relations among Stiefel-Whitney classes. So that that we've done. So so to show the other implication, first note that we're going to use the classification theorem. Again, that's a key. This calculation is a priori weaker than any kind of universal formula, but part of what we're doing is making use of this classification theorem. The Whitney sum formula holds if and only if it holds for gamma n cross gamma m over the corresponding Grassmannians. You also have to use the fact that the Whitney sum formula holds for internal direct sums if and only if it holds for external direct sums or these kinds of product bundles. So now let's consider the following diagram. Let's think about that gamma n cross gamma m over I'm going to omit the R infinities. And so we're trying to understand this map. There's a bundle map here to gamma n plus m. The Whitney sum formula is just about calculating the impact of this map, the effect of this map, what this map induces in cohomology. But where we're going to try to see this is look at the classifying maps for products of line bundles. Okay, and of course this is just a product of RP infinities. And what we have is, you know, a big product of gamma 1s over this. Okay, and we're allowing ourselves, well, let's look at star prime. So again, we're allowing ourselves that this is injection on cohomology from any Grassmannian to any product. And we're going to use that 3 times. I've got 3 Grassmannians here, Grassmanni of n-planes, m-planes, and n plus m-planes. And so, yeah. So so by star prime, if I look here at, let's do this first, 1 plus W1 of gamma n plus m plus etc. Then this maps to, in cohomology, on using star prime, our assumption that we know this map, to a big product of 1 plus xi, where I equal 1 to n plus m. But we can also look at this calculation in intermediate stages, in the middle stages. So we can look at 1 plus W1 gamma n plus etc. And that's also going to go to a product. And we can look at this. And the point is that that's going to go to the second factor of RP infinities. That's how we've defined the maps. Maybe I didn't say that, but we're going to classify these products of line bundles on the individual Grassmannians first. And then because, exterior direct sum is associative, I don't know if we've proven that, but that's a very useful fact. Then we have that that this diagram commutes, and then again, this is star prime used 3 times. Each of these, now this goes from I equals n plus 1 to m, 1 plus xi. But we see that then just manifestly, the total Stiefel-Whitney class of the universal n plus m plane bundle maps to the same place as the product. So we see that the total Stiefel-Whitney class of gamma n plus m has the same as the total the product of total Stiefel-Whitney classes but because all of these maps are injective, so they have the same image, of course, in. This is a calculation in the cohomology of of a product of RP infinities. So then because the Because these maps are injective, then they must agree in the middle, in the So here we're using both the classification theorem and actually the fact that we have calculated the cohomology of Grassmannians. So we're sort of bringing our major results together in order to know that these are injective. So we're not just mapping them somewhere, but there might be a kernel showing that maybe they differ by something in that kernel. And but that's the result. So what this really says is that once you have both the classification theorem and you've done the work to calculate the cohomology of Grassmannians, then you have this calculation that that both you use in the calculation of the cohomology of Grassmannians, namely looking at the Stiefel-Whitney classes of the universal bundle gives rise to symmetric polynomials, but that calculation can be used again to establish Whitney's sum. That's what this argument is. I want to give this a name. Well, I want to call this a weak splitting principle, or first splitting principle, or something like that. Or maybe with the usual splitting principle, you know, just another part of it. But again, it's what the splitting principle is there's a specific theorem about how you can, which allows you to reduce some calculations to calculations for products of line bundles. So that's exactly what we're using here. So call this technique that we just used a weak splitting principle, or first splitting principle, or case of the splitting principle, or something like that. I don't know if we'll cover this the usual splitting principle till later, but I wanted to say this is a case of that reasoning, because what we showed is what we were able to do is deduce the Whitney sum formula for any bundle, first through universal example. Well, that's all fine. And then because this classification map is injective, we were able to reduce it to a calculation in the cohomology of a product of RP infinities, and it's a remarkably simple calculation, namely the product of 1 plus xi from I equal 1 to n, along with the product from I equal n plus 1 to m, is the product over the whole set of indices I equals 1 to n plus m. So it's a immediate calculation in the cohomology of a product of RP infinities, but it implies Whitney's sum in general. Again, assuming this injectivity, which I'm calling a case of the splitting principle, or weak splitting principle, or I haven't decided yet. It's not standard terminology. Okay, so so now, in light of this, wouldn't it be nice to prove star prime? But we're going to focus on star. That this map sends the ith Stiefel-Whitney class of the Grassmannian to this ith symmetric polynomial, or in other words, really just what are the, which is really just calculating Wi of the product of line bundles. And one key is going to be finer control. That for this calculation, I want to make this calculation, I want finer control of the homology and cohomology of a product of RP infinities. And this is a basic calculation that I think everybody manages in a first-year algebraic topology course. But I want to just give some, maybe not even finer control, but just names. So we have that the cohomology we've been saying is a polynomial algebra on x1 through xn, if this is a product of n copies of RP infinity. And what we're going to do is also think about the homology. So in homology, I'm going to let B, I, K be the non-zero class in the kth factor of RP infinity in degree I, and then included in the homology of the product. And by abuse, then, well, so we're going to take the image of this as, well, yeah. Actually, no, let me just have it on that factor. So it's helpful to use multi-indices here. So let I be a sequence of n integers and define two classes, one in cohomology, one in homology, through those multi-indices. Xi is going to be the product, x1 to the I1 cup product, xn to the in. Whereas bi, so cup product, one of the main things you prove is that cup product in a, this is the multiplicative refinement of the Kuhn theorem, cup product corresponds to the sort of tensor product in Kuhn. And here we're going to use that in homology. So I've got B sub I1. So that's like an RP I1 on the first factor. And we'll use the cross symbols. Could also use tensor, I suppose. Yeah, maybe I'll use tensors. B, I, N on the nth factor. And Kuhneth implies these are Kronecker dual. So if I want to understand any homology class, I can evaluate X upper I as I, you know, let's let as I vary over things with the right degree. That's the right total degree is what I just defined there, just the sum of these indices. And similarly, if I want to see what cohomology class I have on my hand, I can use various B sub I, evaluate the cohomology class on those, and it will determine, in fact, because these are Kronecker dual, the way this works is that the coefficient of x to the upper I is going to be the value of my cohomology class, however I get it, on B lower I. Okay. So let me we're now going to go, I did some work ahead of time because there's a lot of writing. I'm going to okay. So what we're going to do, let me actually go up from this. So the calculation we want is of Wi of a product of line bundles. If we can do that without the Whitney sum formula, we can, as we just did, deduce the Whitney sum formula. As well as, I mean, you have to, the right order is to do this calculation after the classification theorem. And then you get that, and also after getting then you also need a cell structure to prove injectivity, and then you can get Whitney sum. So we're going to use the definition. We're going to generally think about just these dependence varieties rather than their resolutions. I'll say that again a few times. So let's do a warm-up example. Let's consider W1 of gamma 1. That's something we're supposed to do via axiom. We already did. And the axiom says, let's just look at over RP2, and we're going to play these games. We're going to use as many or as few coordinates as we want. So again, a careful accounting of this would make sure to check that you've got isomorphisms and cohomology wherever you need. So the cohomology of RP2 into cohomology of RP infinity, or that quotient, is an isomorphism through degree 1, in fact, degree 2. And we did this by taking a section. So this is the Euler class. So is represented as a tome cochain by the vanishing of a section. And here's the change in perspective, namely that after doing this work with Schubert varieties, so we note that gamma 1 sits inside RP2 cross R2 as a vector bundle, and we can use, the coordinates here. So, so the point is, with vector bundles, you only have local coordinates. But if you have something embedded in an ambient bundle, I mean, our Schubert cells, for example, were defined by where this, where the n-dimensional subspace of R capital N or Rm, how it intersected various things. So that was using the coordinates in that trivial bundle. So what we can do is, for example, define a section by projecting the coordinate E1, call it, in R2 onto the L, which is the fiber, the fiber of gamma 1 over a point in RP2. So let me just draw this picture. So the one way to think about gamma 1 is, it's the total space of the collection of lines through the origin. So it looks like that. Of course, as a space, then you have to blow up the middle, but this is sort of part of how we looked at gamma 1 for various, even the definitions. And we've got the vector E1 here, and its projection onto this fiber itself, where it lives, would be itself. But otherwise, you take orthogonal projection, and for each of these lines through the origin, that is going to get shorter and shorter until, for the vertical line, you would have a 0. Let me make these bigger. So these are the projections, and that makes a section. And then as I go past vertical, it starts growing a little bit and comes back. Now in this picture, it's harder to see that it quote unquote dips below 0. So there's our standard version of the Mobius bundle. But I just wanted to give you a little bit of the geometry. We're fixing a vector in R2. We're projecting it onto each, and that vector is sitting in a different R2, if you will. It's over the fiber over on L. And I'm using that copy of E1, but it's, quote unquote, the same everywhere. That copy of E1 to project onto the L and get the value of the section. Okay, so now we're gonna, because there was a fair amount of writing, I prepared ahead of time. So we're going to consider this product of line bundles. What we're going to do is we're going to take n equals 4 as an example. I think, well, we'll see that the general case will make sense if we look closely at this one. Again, it's the fact that this product of line bundles sits inside a trivial bundle. This product of line bundles, again, instead of over RP infinity, I'm going to think about it sitting over a product of RP3s, which sometimes I'll call RP3, or I might call P of R4. So it sits over that product, and then by definition, this comes as embedded in this trivial line bundle. It's a trivial line bundle of rank 16 because every line comes in R4. And then so the external direct product is a rank 16 vector bundle. And what I wanted to do was put coordinates on this. So really what we have is, this is a space of 4 lines. We're then going to take their span to make the vector bundle. Those 4 lines, let's just call them L1 through L4. These are just 4 points in gives you a point in the product of RP3 with itself 4 times. And let's give those lines names in full coordinates. I find that this is helpful to use coordinates. So L1 is going to live in the first of those 4 copies of R4. Let me make this clear. So let's just call it ABCD sub 1. They're all going to be unit vectors. So ABCD is has a squared plus b squared plus c squared plus d squared equals 1. And then it's going to be 0 on all other factors. And the way I want to say that is I want to call that, let me write and call it a, b, c, d sub 1, because it's lives on that first copy of R4 within R16. And then next, we've got what we'll call E, F, G, H sub 2. We have I, J, K, L sub 3. And I decided to, because we're already using M and N, and O looks too much like 0. I guess we were using L as well. But anyways, P, Q, R, S sub 4. And these are all unit vectors. And again, the direct sum that we're looking at, so the external direct sum, which we've denoted with cross, but it's, you know, external direct sum, just means taking the linear combinations of these. I've got one vector in the first copy of R4, another in the second, another in the third, another in the fourth, and then I'm looking at all linear combinations, and that's how I get a plane. Okay, so that's what we're going to do for coordinates, and we're going to make our sections by projecting. And we're going to use the fact that projecting onto, so note that these are orthogonal. So here's an important note that, so note that, important note, these are orthogonal, right? They have different supports. One is just non-zero on the first 4 coordinates, one is just non-zero on the second 4, et cetera, et cetera. Okay, so from our definitions, what are the different WI? Well, W4 is a vanishing of a section. Let's call it S. Or let's call it S1 in anticipation of what other work we're going to do. So S1 is going to be a projection of this vector, which I'm going to call the direct sum of 1, 0, zeros. It would look like 1, 0, 0, 0, 1, 0, 0, 0. So it's the direct sum of E1s as well. And it's going to project onto that span, which is the fiber. And well, the projection of a vector onto the span of orthogonal vectors is just going to be the sum of its projections. So that's a great thing about orthogonal frames, or more generally any orthogonal spanning set. I can calculate projections. And for example, this coefficient A is just the A, B, C, D sub 1 dotted with this, I'll call it plus E1. Of course, you only need to look at the first of the 4 factors of E1, that first 1, 0, 0, dotted with A, B, C, D is A. So these become pretty immediate calculations. I have A times my first basis vector plus E times my second orthogonal basis vector plus I times my third plus P times my fourth. I'm just picking off the first coordinates. Well, assuming transversality, and we're just gonna make that blanket assumption. That's not something I want to check. We would need to write this up carefully, get it accepted into a journal or something like that. But for now, let's just assume transversality, and then say that, okay, well, we know then that our top Stiefel-Whitney class is represented by the places where that's 0. And I'm calling the places where that's 0 X sub W4. And Well, that's 0 if and only if A, E, I, and P are 0. But what does it mean for A to be 0? Well, A, B, C, D is the copy of R4 that L1 is in. And for A to be 0, instead of anywhere in R4, just picture an R2, that means your X coordinate be 0, you're up there, R3. If your X coordinate is 0, if you're sitting inside the subspace with X coordinate 0, you're sitting inside a copy of R2. So here we have that L1 sits inside the subspace of R3. So it sits inside a R3 inside R4, where the first coordinate is 0. And similarly, L2 sits inside a copy where the first coordinate is 0, et cetera, et cetera. But now you just remember that the cohomology of projective spaces, H upper 1 is represented by any codimension 1 linear subspace, among other things. So if I just consider in my my copy of RP3, if I consider in my copy of RP3 this condition that Li sits inside the first coordinate 0 subspace, which is a copy of R3 inside R4, that means that that's exactly in that cohomology of that RP4. That's X. That's the generator X for that copy, X sub I. So if my L1 is, let's call that vertical. If my L1 is vertical, L2 is vertical, L3 is vertical, L4 is vertical, I get the product of the xi's, x1 times x2 times x3 times x4, and that is what we were calling sigma 4 in this case. So that's just applying the definition. Of course, this is the Euler class, and we expect the Euler class to be not so bad. But now let's look at W3. And I will make this even smaller. So W3 is represented by the dependence of 2 sections. So what we can do is, again, we can take the S1 section is going to be plus I E1. This is going to be plus I E2. And once again, I just project, but if I am assuming that my L's are unit vectors, then they're on different copies of R4, so they'll be orthogonal. So I can calculate that projection just through a dot product, but my EI dot products are simple to calculate. In the first case, I get all the first coordinates, A, E, I, and P. In the second case, I get all my second coordinates, B, F, J, and Q. And so those are my 2 sections. And next, what I want to do is, because I'm only seeing those first 2 coordinates, I'm going to restrict this whole picture to, instead of a product of RP3s, I'm going to consider a product of RP1s. So that's pretty minimal in there. So, and then you check that the cohomology that we want is isomorphic in that degree. Let's see. I mean, now I'm thinking that there's actually something more to say there, but we'll let's stick with just this focus on the first 2 coordinates. Then these are dependent. These 2 vectors are dependent. Well, we see that they're dependent if and only if, like, the ratio of B over A is that of F over E, is that of J over I, is that of Q over P. Oh, that means that those 4 lines were the same. Okay. So we went from the dependence of sections because we chose these special sections. We're able to find the conditions on the lines that give rise to dependent sections. And in this case, it's that those lines are the same when I really think of them inside of P of R2. Now, the idea would be in P of R4 would be that they would project onto these, but let's continue to just think in terms of P of R2. So now we need to, let's just call this X sub W3. This is the dependence locus for two sections. And this is X sub W3. And what we would really want is, the other technical thing here is we would want to make this somehow smooth. So we'd make a hat. Actually, in this case, wait, this is a diagonal, so this is still smooth. The next one we would need to work to make smooth. We can evaluate on an H3 basis. So again, here's where we should perhaps stick to RP3 instead of RP1s, because we have the B3 on the ith factor. But what does this mean? So how would we evaluate? So it's B3 on the ith factor, but let's call it B3 on the first factor. Let's just do a concrete case. And then you really, let's be clear. So evaluate this tome class, which is represented by all four lines being the same on B3 on the ith factor across B0 across B0 across B0. That's an RP3 cross RP0 cross RP0 cross RP0. And so what we're really doing is fixing three lines, and I'm going to think of them as generic. And then the fourth line is going to go over all possibilities. It's going to, point in all possible directions. And we're asking for when they're the same, but obviously if I pick my three lines generically, that never happens. So generically this, so because these three lines, so these are my L2, L3, and L4. So L2 not equal L3 implies that this B3 in place one cross B0 cross B0 in places 2, 3, and 4 does not intersect X W3 nowhere. And so that implies that that evaluates to 0. And then the point is that if yeah, so then what you need is again, now I want to be switching back into the key calculation. Similarly, the middle one is 0 because I will have two factors of the b's that are allowed to with whose corresponding lines are allowed to move around. But so this is my picture of L1 is allowed to move around, L2, L3, L4 are fixed. For B1 cross B1 cross B1, again, here we want to be in RP2, or sorry, RP1 for B1 I cross B1 J cross B1 K. Let's even do 1, 2, 3. We're in R2, so that means these B1s I've got my L4. So we're going to calculate in P of R2. This is my L4. It's fixed. Or maybe let me draw. This is my L4, which is fixed. Oops. And then L1, L2, and L3 can move around in all sorts of possible ways. And we see that exactly once do L1, L2, and L3 coincide with L4. So, and transversality is again straightforward. So L1 equals L2 equals L3 equals L4 exactly once. Okay, and so what we see then is that we deduce, so the only non-zero pairings are with all of these B1I, B1J, B1K, and I guess you can say B0L for various permutations. And by our choice of basis for homology and cohomology of RP infinity, or of products of RP infinities, or in this case of RP4s, so that implies that the tome class for XW3 is, well, it's sigma 1, sorry, it's X1, X2, X3 plus X1, X2, X4 plus X1, X3, X4 plus X2, X3, X4, which is sigma 3. Phew. So that's what we can do. It's 2 steps. We've identified this locus of dependence. In this case, that locus of dependence of the sections ends up being the subspace of a product of RP 4s, which is, or RP3s, which is what you often call a diagonal. In fact, this also, in general, the diagonal is going to go to some, well, this is a thin diagonal. So anyways, this is analysis that you can make in general, but we go ahead and pair explicitly with our homology, and we find sigma 3. Okay. I'm going to go on. You can pause for a little bit, rewind, look through that. W2 is represented by dependence of 3 sections. Again, I want to, quote unquote, hat that. I want to think about this is a 4-dimensional bundle. For 3 sections to be dependent, that means they would span a plane inside the 4-dimensional space. And I want to look at that gamma 2 construction. But I'm not going to go through those details. Just want to show where the analysis will head. Once again, to make those sections, what I'm going to do, because this bundle sits inside a trivial bundle, that means that, again, I don't have good coordinates except locally in the fiber itself, but I do have good ambient coordinates, and I'm going to use those. I'm going to take my EIs on the various factors, and then I'm going to direct sum. So I'm going to look at 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0 as a vector I really like to use inside of R16. And we're going to make sections through projecting those, okay? And so then, and then I also want to just look inside on RP2, not the full RP3. Once again, we would need to do a little more argument to show that this is a valid restriction. But with notation as above, when I project, well, we already calculated the values of E1 and E2 when we project. That was just A times AB plus E times EF. Well, if I've got a basis and I'm writing it out to the right, I'm just going to use a row vector. So I've got A times ABC plus E times EFG, etc., plus I, and I'm just going to call that this row vector AEIP. And if I want 3 sections when they're dependent, that means that these 3 row vectors are dependent. And again, what I mean by that row vector is I'm looking inside the span of 4 lines, and I'm taking these particular linear combinations, A times my first basis vector plus E times my second, plus I times my third, plus P times my fourth. And then within that span, I want to know where things are dependent, okay? And well, elementary linear algebra comes to play and says, if I've got this matrix of 4 by 3, let's see, or no, 3 by 4, 3 columns, 3 rows, 4 columns, 3 rows by 4 columns matrix, those are dependent. That means that it's rank 2. Well, less than or equal to 2. This is again where some additional, sometimes we might need to blow things up in order to have some things that are smooth. But let's think about this being rank 2, and that will happen if and only if those the column vectors span a rank 2 subspace. But those column vectors are exactly the lines, the unit vectors that define the lines. So I want to know where my 4 lines span a rank 2 subspace. Let's call that X sub W2. You might notice something here. Before I wanted my 4 lines to be equal, that means that they span a rank 1 subspace. We'll talk about that in a second, but then what we would need to do is evaluate the Thom cochain associated to this this condition that L1 through L4 span a rank 2 subspace on the various, on, for example, B2 sub 1 times B0 times B cross B0. Again, because this is in degree 2, but then also, and then we have all the permutations there, and we also have B1 sub 1 cross B0, sorry, B1 sub 2, B0, 3, B0, 4. And let's think about that geometry. We have 2 generic vectors. This is happening, I think, in an R3. Once again, that's some arguing that we need to do. So we have L3 is fixed. L4 is fixed. I'm thinking of them as generic. they span some subspace. L1 and L2 are able to move around in one dimension. So L1 can kind of spin around in one dimension. Maybe L2, I might want to make these generic, but the point is then that each of these, as L1 spins around in one dimension in R3, it will intersect the span of L3 and L4 exactly once. So L2 will be in the span of L3, L4 exactly once, as will L1. And so that means in this product, this B1 factor 1 cross B1 factor 2, that's an RP1 cross RP1 inside this product of RP. I guess I'm thinking of these as RP2s at the moment. That RP1 cross RP1 is going to cross this plane exactly once. Cross this X sub W2 exactly once, when those representing circles that are the unit vectors on the L1 and L2, when they cross the plane exactly in 2 points, but of course we're identifying those as an RP0 of intersection. And then similarly, so this implies, once you have transversality, that this equals 1, and similarly, there's no special, this is symmetric. All of these are symmetric. So once I do one case of B1 cross B1 cross B0 cross B0, I also have, for example, B0 cross B1 cross B1 cross B0. And this, let me just make the claim that that's 0, because 3 vectors are generic. They will always have, and they're not moving, their rank is always going to be 3 or greater. So we see that those 0 parts of the calculation are quite easy. The 1 parts of the calculation aren't bad either. And so what this means is that this tome class is like x1, x2 plus x1, x3 plus etc. We end up with x3, x4. Those are all the possibilities. We have our B1 cross B1s. They're dual to these xi times x sub I times x sub j. And this is exactly our sigma 2. And that's what we wanted to prove in that case. Okay. So next case, I'm going to be very brief. You might add in recording, but so we'll next see, consider this an exercise. Next, use SI equals the projection of a direct sum of EIs. And then what we see is that to get our sections, and we will you deduce that these are dependent if and only if all the LIs are dependent. This is from I equals 1 to 4 together. So I've got 4 lines in R4. We really don't want to restrict to a smaller projective space now. We want to look at lines in R4, and those are dependent. And you now, so that's our x sub W1. You now evaluate that on the various B1s. and see that X sub W1 on this cohomology class on all of the B1s, really B1 cross B0 cross B0 cross B0, etc. And that's because if I have L1, L2, L3 are generic in R4, they form a three-dimensional subspace, then L1, I'm just picking a one-dimensional space for it to circle around in. And by, say, picking a plane there, and exactly once will that intersect the span of L1, L2, and L3, or maybe I said, maybe I used L1 twice, so let's call this L4. So, and so we see that we get sigma 1. And that proves the theorem in this case. And what do we see in general? We can really think of this as two parts. So theorems, sort of in proof, there's two parts to it. First, that that Wi is represented by the subspace of product of R P, and this is for I less than n. The Euler class is always going to be special, but Wi is represented by that subspace of Rp. Let me just call it K for the right K, so that the Li have rank let's see, so W3 was rank 1. Well, let me, rank n minus I. Let's really say it's going to be the hat of that subspace. So there's going to be a smooth object sitting above it. And then that this subspace of a product of RP infinities, RPKs, and it's the smooth resolution of this subspace represents sigma I in cohomology. That's what we've seen for 4 dimensions, and just organizing our thoughts, putting through more details, etc., would give it in general. So I'm going to stop there.